Okay, so we're looking at page 151 in the book, and it talks about at the bottom group number and valence electrons. So valence electrons, when we talk about valence electrons, I'll let you guys tell me what valence electrons are, because it says what they are. So what are valence electrons?
Electrons in the outermost energy level.
So it's the electrons in the outermost energy level. So I'm going to go ahead and do phosphoruses. This is review, okay? So if you did not do well on your test, or quiz that was 24 or 25 points, please come in and get help. That's all I can tell you. We're moving on. You guys need help? Want help? I'm here before school. I'll help you. I'll give you some examples. I'm here after school. My time is your time. Come in. Okay? Because we're moving on. We're going to review it, but sometimes people need more than just reviewing to do that. So when we look at phosphorus, we're going to write out the abbreviated version, and this is what you did on your quiz. And so some of you were really successful at doing those, and some of you struggled. And you can't do that on the test because you're not going to probably pass the test if you continue to do it the same way as what we did on the quiz. So a phosphorus is going to be neon, and then it's going to be 3s2 and 3p3. Then, if you guys remember, we did something new that wasn't on the quiz, where we did orbital notation. Okay. Does anybody remember why each of them get their own orbital? What's the reason for that? Yes?
Because they don't like to pair up.
Yeah, because if they pair up, their electrons repel, right? So it's like putting two people in a room that don't like each other. You're not going to probably put them in the same room. Like if I'm making like when we go on wrestling trips and we stay overnight, I am not going to put certain people together. That's not going to work. Nope, we're not going to put them together. That's not going to work. It's going to be not good for the other people in the room. All right? So unless we have to pair them up, we'll do that. Electrons are the same way. If they don't like each other, they're going to want their own space, and that's why you do them. And they all have to have the same spin. So if you show them they have the same spin, that also reduces the level of energy needed. So that's just, it's called Hund's rule, and I'll probably give that definition to you later. But there's an easier way to do. By the way, going to this definition, how many valence electrons does phosphorus have? 5. The outer layer is the 3, right? It's not the outer sublevel, but it's the outer level. So the outer level is the 3, and so there's 5 valence electrons that it would have. Now there's an easier way to do this, other than to write this out every single time. So if I give you a couple examples, I say, hey, how many valence electrons does, say, bromine have? And I don't want to go through this abbreviated electron abbreviation unless I have to, and I really don't want to. So I would ask you that one, or I might ask you how many does tin have? We'll do 2 of them. So we never include the D's. They're never outer, because they're always going to be inner when we put them into our abbreviated version. So we're only counting S's and P's, so how many total would that be? How many total electrons? If that we would have the most electrons, you can even use this example up here. So if we filled all those up, how many is that going to be? 8. That's all you can have is 8. 1 through 8. So what you do, if you guys remember, you just count across the period, excluding the D's. So bromine's going to have how many? 7, right? You count across, 1, 2, skip D's, 3, 4, 5, 6, 7. Now we're at bromine. Now, if we're going to indicate that, we need to indicate it just like we would with the orbital notation. So we go 1, 2. What are those? Those are the S's, right? And this is P1, P2, P3. Now we have to start pairing them up, right? It's like doing the arrows. So this would be like, phosphorus would be like bromine right now. We just have a P in there, and that's what would be phosphorus. But bromine has to add 2 additional ones to get to 7. So 5, then you start pairing them up. 6, 7. All right? So bromine would look like that when we do what's called electron dot notation. They say Lewis symbol. So they say, go ahead and draw a Lewis symbol. That's what this is. This is a Lewis symbol. My terminology sometimes is based upon the last book, and they do some things different, but that's called a Lewis symbol. Go ahead and do 10. Go ahead and draw 10 out. This also represents the valence electrons. So if you count them, there's 7. So bromine has 7 valence electrons. If you had your choice, you would want a lot of these on the test. But you don't get a lot of them. Sorry. Because they're easy. Got to put some easy ones on there. Don't take a whole lot of time. And these don't. So 10 is how many does it have? Has 4. So you go 1, 2, 3, 4. You're done. Okay? Because that's what 10 is going to have in its outer level. Why are we concerned with that? Because we're going to look at bonding. When we look at bonding, bromine is going to gain 1, in which to become 8. 10 is not going to gain. It's a little different. It's a metal. They tend to lose. So that's probably going to lose 4. And then it will get its 8. But don't worry about that now, because you don't need to know that for the test or anything like that. It's something we build upon later on, and you have to know Lewis symbols before you can build on and know how many gains or loses. Any questions on that? All right. Something new and different. Again, I think this will be done. Discussion about 9:30. We won't have a discussion after that point in time, and then I'll let you guys work on your assignment. Turn over to page 154. 154. Okay, so give me a couple periodic trends we already know on the periodic table that we've discussed already. Some really simple periodic trends. So give me a periodic trend for a group and tell me what the trend is you're looking at. So what's a group trend? Really easy. Just don't make it too complicated. Look at numbers and tell me a group trend. Group is a column. Yes, Andrew?
The first group is plus 2 plus 8.
Right, they're going to add protons at a rate of 2, 8, 8, 18, 18, 32, right? So the group trend is specific, and you can make a prediction of what the next element in a group is going to be based upon the trends that happen on all the numbers. So that would be a good trend. That's really specific, and the reason for that trend is because of the levels, right? Because it goes 2 in the first level, 8 in the second level, 18 in the third level, so on and so forth. Okay? So you could give me a reason. You go, oh, Mr. Garland, the reason is because, remember, the first shell has 2, and the next shell has a total of 8, so there would be an increase of 8, and then the next shell would be 18, and then we'd increase by 18. On that. So what's a period trend? That'd be really easy. Yes?
Increase by 1.
Yeah. So the atomic number increases by 1 as you go across a row on the periodic table. And the reason for that is because you're adding 1 proton to the nucleus each time. So that's a really easy trend. Weight, we can look at weight. The weight increases going down and it increases going across. So that's another easy trend to do. Well, this was an easy trend too, but the reasoning behind it, you'll have to do a little thinking, but once we do the thinking and write it down, it's pretty easy to understand. So the first thing we're going to look at is atomic radii. And all this it indicates the size of the atom. A neutral atom. Okay? Now, they don't give you numbers, but they could give you numbers, and it would correspond to the sizes that we see on page 154. We're not looking at reds. The red ones are your D group. So we're not looking at the D group. We're only looking at the S's, which are the yellows on page 154, and the greens that symbolize the atomic radii, relative atomic radii. So these are all relative atomic sizes and relating to one another. So let's just go ahead and just look at our group. So what's the group trend? What do you guys see? Going down each group, what's the trend for atomic radii? Faith?
The size increases?
Yep. So the size of the atomic radii increases going down a group. Can anybody, I think there's some individuals in here, they're willing to can tell me the reason. Because every time you have a trend, you probably have a reason that you can come up with, an explanation. Why does it get bigger going down the group? Can anybody explain to me why that happens? Yes?
More protons.
Okay. All right, so we could use that so that's, I want to encourage you guys to give me reasons for that. You can say, well, there's more protons. What makes up the size of the atom? Remember, we look back. What determines the size of the atom? Protons or electrons? Electrons. So we could say protons, but they don't indicate the size. It's only electrons that do that. So, sorry to shoot you down on that, but I mean, that's a that is what happens, though. It does get more protons. But that is just a fact that doesn't support the reasoning for the size. Anything else? Yes?
The electron cloud gets bigger.
Yes. And why does it get bigger? You're right. Well, you're basically saying it gets bigger, but we already know it gets bigger because the radii says it increases. So it's just another way of saying, you're just saying it another way. You're just saying, but why does it get bigger? Why does the cloud get bigger? Now, you guys should be able to remember when you go down a group, when we look at each group, like for example, sodium. Sodium is, I can do sodium real quick. It's 1s2, 2s2, 2p6, 3s1. Then if I go down one more, I go to potassium. Potassium's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Does that tell you something just with those two? What's happening? What can you say for the reasoning? Okay?
It's affected by the attractive forces of the protons in the nucleus.
Nope. I think you're looking at period, and that comes later. Yes, Billy?
Is it more sublevels?
Kind of. Almost there. Yeah.
Is it like the valence electron thing, like, where it is, so that's just something?
You're okay. And you're right there. I think you're right there. And I think if you would know how to present it and say, what do we look? We look, they're in the same group. So this is a 3s1 and 4s1. What do you know about the fourth level versus the third level? Yeah.
And they're further from the nucleus.
Right. So what are you doing? Each time you go down a group, what are you doing?
Getting rid of the nucleus.
Right. And why are you getting further away from the nucleus? Because you're what?
Losing.
Because you're adding a level. Right? Each one you go down, you add additional level. And we know that levels get farther from the nucleus, right? So the next one, K, what's it going to end, or RB, what's it going to end in? I'm not going to do all the ones in between, but what's it end in? 5s1 is 5 farther from the nucleus than 4. Yeah. We just add on. So the reason for that is additional levels down the group. Okay, so the reason is that additional levels are added down the group. Okay, all good answers. I mean, you're thinking adding protons, but then when you get in specifics, you go, wait a second, that's in the nucleus and it's really small, so that's probably not the reason. And then you say, well, adding sublevels. Yep, you're adding sublevels, but that in itself doesn't mean that you're going to get bigger, because you're adding sublevels as you go across. If you go to 2s2 to 2p6, you're adding a sublevel. So what's important is you're adding a level each time as you go down a group. And then you go, oh yeah, that makes sense, because adding a level means it's further from the nucleus. So sometimes you look at your reasoning, if you know more specifics about it, it'll help you either say yes, that makes sense, or no, that doesn't make sense. Okay, so the group trend is to get larger going down because, reason, you're adding additional energy levels down the group you're adding. Okay, one's a little bit tougher to see is the period trend. So period trend. So what's the period trend? That one's easy to see too. What's happening going across the period at the size of the atom? Again, we're not looking at these. We're only looking at yellows and greens. So what's the period trend? What's it doing? Is it getting bigger, getting smaller, staying the same? Yes, Faith?
It gets a little smaller.
Gets a little smaller. Not to the, I mean, it's not super noticeable, but as you go across, the general trend looks like it's getting smaller as you go from left to right, right? Okay? So the trend, period trend is atomic radii gets smaller. All right, this reasoning is a little tougher to explain. Why would it shrink? Because what are you doing as you go across? What are you doing with the electrons? Are you adding electrons as you go across? You are, one at a time, right? So when you go from sodium to magnesium to aluminum, you're adding. What do we know about electrons? They'd like to repel. So common sense says they should get bigger, right? Because they repel. But what else are you doing going across? What else is being added? Not only electrons, but what? Protons, right? You're adding an additional proton each time. Now, but you're not adding an additional level each time you go across. You're adding electrons to the same level, right? So it's kind of like a magnet that gets stronger and stronger and stronger. The protons in the nucleus you add more and more. And what do we know about the protons and the electrons? What's the relationship between them? They're attract, right? Opposites attract. So if you're adding electrons to the same level and then also adding protons, you can see why it will shrink. Because the addition of the protons will cause a stronger attraction between the nucleus and those electrons in the same level. So that's the reason why it gets smaller. It gets smaller, and its reason is so the reason is protons are added to the nucleus, creating a greater force of attraction between the electrons in one energy level of electrons. Not multiple, but that one energy level that's getting shrunk down. Okay. We'll come back to that reasoning and that, but that's what when we talk about trends, and that's all we're going to do. They also just talk about ionization energy, and we're not going to do anything with ionization energy. We're going to save that for you guys to do later. We're not going to do it for this example. So, your assignment that I have come up for you to do is the following, and if I can find what I did with that, I'm going to give that to you. So, rest of the time you can spend working on this, page 151. Tomorrow I'll go through some specifics on the lab.
Is it just what's written right, like here?
What's that?
Is it what's written?
Yeah, is it the 151, 44, 46?
Right. I'm going to write this for those who are tuning in the assignment. But yeah, it's page 151, 44, 48, 50. And I think 44, you just have to pick out 2. You don't have to do them all. So there's 4 of them on 44 that you'd have to do originally. So pick out 2. I don't care what 2 you pick out. And then page 156, have you do 58, 60, 62, and 64. And then we'll talk about those tomorrow. So I went a little bit over what I thought I would. But you guys still have 15 minutes or a little more in which to work on that assignment. Let's just look at it really quick. 44, you just have to write abbreviated version, and then you got to show the lines underneath. So 44, you have to do the abbreviated version, and then you have to show your lines with the arrows. Okay, that's what they say when they say blocks. Use the sublevel blocks. That's the lines. They use blocks. You can use lines. All right, for 44. 48. 48 is just information about using the sublevels and the arrows and blocks. So do your best on 48 and 50. Those are a little bit more demanding questions, but they're one-answer questions, and do the best you can on it because it's a completion grade. And then you go to 58. 58 will basically, you have to just tell me how many valence electrons you have, like 1 through 8. You don't have to draw the symbol with the dots. And then 60, you have to draw the Lewis symbol with the dots. And then 62 and 64 have to do with larger. You have to predict which one's going to be a larger atom based upon the trend. So 62 and 64 is using your trends. So basically, you're using your group trend. you're saying which atom's bigger, magnesium or strontium? Which one's bigger, magnesium or strontium? Based upon the trend. Strontium, right? Because the group trend is to do what? Get bigger down the group. If I ask you which one's bigger, strontium or iodine? Nope. Strontium. Because what's the trend going across? It's smaller. So, as you go across, iodine's smaller than strontium. So you got to use your trend, like, oh, okay, they're in the same period, the ones on the right are smaller than the ones on the left. If you're doing group, oh, the ones up above are smaller than the ones down below. So I ask you which one's bigger or smaller, then you should be able to use that trend in which to get that information. So.